So today, in the first video of our analog and digital electronics, we have seen about the number systems and the gates. Now today we will learn about the algebraic methods, the Boolean algebra. My name is Shivcharan Puri and I'm an assistant professor in the department of ECE, Asansol Engineering College. So fundamentals, you see here. So the postulate, basic postulate, from that basic postulate 1 says a Boolean algebra is a closed algebraic system containing a set K of 2 or more elements and the 2 operators, this one and this one, and or we will see. Postulate 2, you see here, A plus 0 is equal to A, okay, A into 1 is equal to A, okay, existence of 1 and 0, okay. Commutativity, A plus B is equal to B plus A into B is equal to B into A. Associativity, A plus B plus C is equal to A plus B plus C. A into B into C is equal to A into B into C. Distributivity, you can see here, this is the distributivity. And here's the complement, A plus A bar is equal to 1, A into A bar is equal to 0. This one. Idempotency, you can see here, A plus A is equal to A into A is equal to A. Null, A plus 1 is equal to 1, A into 0 is equal to 0. Involution is equal to A. So double inversion is results in the same variable. Or and complement property, A plus 0 is equal to 0, 1. A multiplies 0 gives 0, A into 1 gives A. 0 complement is 1 and 1 complement is 0. So these are the basic things we should know before the starting of the digital electronics section. Absorption, A plus AB is equal to A into A plus AB is equal to A. Here you can see here, if you see this first video, you can see here A plus 1 is equal to 1. So if you put here A common, 1 plus B will be remaining. So 1 plus B again 1. So A into 1 is equal to A. So in this way you can prove all the fundamentals of the Boolean algebra. Okay. So this is an example. It goes with the same thing. A plus A bar B is equal to A plus B. Look at this example. Okay. If you simplify, it will come with the same thing. Now you see here, AB plus AB bar is equal to A. How? You take A here common, B plus B bar is again 1. So it will result in A only. A plus B into A plus B bar. So you can see here the one is a simplified simple form and another is a complement form of a variable. And if you multiply this, it will give you the A. Okay. So if you multiply, you will see that all the theorem 1 to 5 or 1 to 6 will exist. And if you simplify, you will get here A. So you can simplify it by yourself also. So you can see here, this is a theorem 7, A plus AB bar C is equal to AB plus AC, and A plus B into A plus B bar plus C. You can see here just terms are coming, which will give you this plus this, okay, this plus this into this plus this, okay. So it will be A plus B, and you should keep in mind this complemented form should come in the middle to get this reduced expressions, okay. So De Morgan's theorem, which is very important, A plus B whole bar. Okay, if you put the whole complement, it will result in A complement B complement. AB whole bar, it will result in A complement plus B complement. So this is a generalized form. You can see here, these are a few examples which has been done for the better understanding. Consensus theorem, you can see here, AB plus A bar C plus BC. If you get the term like this, so you can see here A, you can see here B and C, you can see here B and C. So in this case, if you get a term like this, simply you can write it in a reduced form as AB plus A bar C. So this term will be gone, redundant. Okay. And in post form, you can see in multiplied form, A plus B, A bar plus C, B plus C. As you can see here, this term will be gone. So it will be A plus B, A bar plus C. So this is called consensus theorem, very important for exam. So as you can see here, the basic way, how to write a function. If AB is equal to A plus B, this is suppose it's a function. There are two variables A and B. Okay. So AB 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. Okay, don't think that 1 plus 1 is 0. It is arithmetic operation. Right now we are concentrating only on the logical operation. So in logical operation, yes plus yes is equal to yes. So therefore 1 plus 1 will be 1. And if you multiply 0 into 0 is equal to 0, 0 into 1 is equal to 0, 1 into 0 is equal to 0, 1 into 1 is equal to 1. And in complement form, you get it like this. So this is the way. So as you can see here, if you want to plot, if you want to look on this expression, AB plus A bar C plus AC bar, if suppose the function is like this, okay, and if there are possibility of this much variable, so you can see here there are 3 variables. To the power 3 is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 combinations, and for that you can get the value like this. You put here the value of 0, 0, 0, and so on. So a way of writing expressions are basically 2 in a nutshell. One is the sum of product, okay, and there is a product of sum. If it is sum of product, you can write it as f of a, b, c, or whatever variables you have. It will be this plus this plus this. Don't consider this one. It can be anything. Okay. The thing is that every product will be odd. That is called sum of products. Whereas in case of POS, product of sum, okay, the product will be, you can see here, there's a sum, and each are multiplied. So it is product of sums. As you can see here, this is, and in SOP expression, remember, you just take down this one. A mean term is a product term in which all the variables appears exactly once, either complemented or uncomplemented. What does it mean? It means that a SOP expression is also represented by mean terms, okay, which is written as this one, small m suffix 0. It indicates that if you are having 3 variables, it indicates that it is a bar, b bar, c bar. That is 0, 0, 0. If it is 1, okay, binary, you can see here in binary code it is 0, 0, 1. That means a bar, b bar, c. If it is 2, 0, 1, 0, it is a bar, b, c bar, and so on. So this is a way of writing a SOP expression in terms of mean term. Okay? So in the if you see this expression 0, 1, 0, that is it is m2, and this is 1, 1, 0, and that is nothing but m6. So it can be written as, it can also be expressed as f1 of a, b, c is equal to m2 plus m6 plus whatever you have here. Okay? So this is the way of writing the SOP form. Okay, sum of product. You can see here, as we are talking, as we are telling here, m2 plus m6 plus so on. Okay, and these are the corresponding outputs. Okay, and some more examples where you can work on. Just remember that after writing these expressions in terms of mean terms, you can also represent this as summation of m, that is mean term, 0, 1, you can see here 0, 1, 6, 7. So in this way you can represent directly. Okay. Now let us consider on POS, product of sum. Now reversely, it is represented as max term. Okay, and here you can see here the a plus b plus c. So it is not 0, it is not 1, 1, 1. Rather, it is, in case of product of sum, it is reverse. So if it is a, it will be 0. If it is a bar, it will be 1. So this is nothing but 0, 0, 0. Okay, and this is odd. So it is represented as capital M0. If it is, you can see here 0, 0, 1. Okay, so this is M1 and so on. Okay, and it is written as pi m of 0, 1, 4, 5, the same way where we in which we have written the mean terms. Okay, and this is the workout of the truth table. Okay, this is more example. Now in case of the relationship between the mean term and the max term, it is represented by this, okay, the inversion. But if you take as a thumb, I mean a shortcut, or rather a thumb rule, whatever is not in the expression, whatever is not SOP is POS, and whatever is not POS is SOP. That means if an expression is given, suppose 0, 1, 2, okay, and if it is suppose 3 variables, so 0, 1, 2 mean terms means you can represent as differently as rest terms will be max term. So either you can represent an expression as a min term or as a max term. Okay, as you can see here, just the representation of the max terms. So these are algebraic formulations. The same thing which I discussed. And you can also use some theorem to basically canonical SOP. What do you mean by canonical SOP? Canonical SOP means standardizing a SOP or POS. Now, how do you standardize? What do you actually mean by standardization of a SOP or POS expression? So you see, you are having expression. Okay, you can see here. Take an example. You can see this expression: AB, AC, AC. So one thing is very sure that in this three expression, and if this is a function, it's a function of three variable. But in all these three terms, there is one variable missing. So a standard SOP will be done if you can just multiply this as C plus C bar, here B plus B bar to get the whole three terms in a term, okay, and B plus B bar. So as you can see here, okay. So if you just do all these things, you will get as summation of m of 1, 3, 4, 6, 7, which is the standard way of representing of SOP. It is also called canonical exam point of view. In case of POS form, what you can do, you can see here a plus b, where gone here, a into a plus c. So it's very evident that it is a function of three variable, but here there is only one variable, and here there is two variable. So simply you need to multiply this as a plus a bar is 1. So you can multiply this as you can see here. So if it is a, you have to multiply b plus b bar, c plus c bar. Why? Because that will be 1 only. Okay, so 1 into a is 1. So in this way you can standardize. So if you whole multiply this, you will get this standard form as like this. Okay. So this is the way, if in the exam they will ask that write in standard form or canonical form. So you have to do all this arrangements to get the final expression. That will be the desired answer. Now this is the don't care conditions. So you see somewhere you will be given the don't care conditions. Now in KMAP we will study in length just to have an overview. So if you have the don't care expression, it will be given as D of 4, 5. So when we take don't care expressions, what happens is that if it is in use or if you have a further simplifying opportunity, then we take don't care expressions or we don't take actually at all. Okay. So this is all about don't care expressions, where we use, how we use, we will see later stage. So as you can see here, this is the electronic logic gates. Okay. Electronic signal, as we told in the previous lecture, that if it is a positive logic, high voltage will be 1, low voltage will be 0, and the reverse will be in case of the negative logic system. It is also called active high or active low, whatever. So as you can see here, the typical the brief of all the gate operation. As you can see here, AND gate, OR gate, NOT gate, and so on. You can see here all the operations here. Okay, and this is as per as IEEE standard 1994. Okay, and in the lab we will see. Okay, so if it's a NAND gate, so you see this is basically ASIC ICs. Okay, and 7400 this is 74 series. So 7400 speaks of quadruple 2 input NAND gate. In that, pin number 1, pin number 2, and you remember one thing: wherever there is a notch, below that notch there will be pin number 1. So this thing you keep in mind, where pin number 1, pin number 2 is the input of the first gate, and 3 is the output. So 1 to input, 3 output. Second gate, 4, 5 input, 6 output. 7 is ground, 14 is VCC. And in this way the arrangement is done. So accordingly you are having digital ICs in the lab also. 7400 series, and 7400 is actually 2 input NAND gate. Okay, and 7402 is a 2 input NOR gate, and so on. So you can see here the arrangements. When we will do the realization in the lab, we have to take these ICs and we have to realize our expression accordingly, or functions accordingly. You can see here, this is a different logic ASICs. As you can see here, this is a basic AND gate, just the brief. Okay, we have already done. This is the OR gate. You can see here 0, and this is a plus operation, and this is the way how we do sum and this one decision. Not get. Okay. If you are using a negative logic, simply you have to use a proper bubble. Okay. So this is NAND. We discussed this in the previous slide. So as you can see here, now we have discussed about the basic get and or not. No? Now let us discuss about the implementation part. So suppose and or not get constructed is if you are having non-NAND gate, okay, and if you want to suppose construct this because NAND gate is also called NAND and NOR are basically universal gate. Why? Because using this gate you can implement any of the desired ICs. Okay, so if this is NAND gate, you can see here AB. So here you will get what? AB whole bar. So again, if you put one or, you can simply get, because this is also a arrangement, you can get here AB. Okay, so if it is inverter, simply you have to short the terminals and you get here A bar. So in this way, by using proper connections, you can implement any function with the help of NAND and NOR. That is what is reflected over here. Okay, and see here exclusive OR we have discussed. Okay, so these are the basic some of the important relationships of the exclusive OR, which is very important actually. XOR gets. You can see here using switching algebra to derive a desired form. So this is the desired form. Okay. So in the if it is a combinational logic, suppose this is a combinational circuit. Okay, you can simplify it using Boolean algebra to get the most simple circuit. Okay, so this is the only way. We will do all these things in the coming slides. Like we will get a big expression on how to reduce using Boolean algebra to get a very simple circuit. This is just a reflection of that. Okay, therefore I am sliding it. Okay, as you can see here, it's analysis of the timing diagram. It is not much in importance in the combinational area, but however in the sequential logic, whether it is a memory based logic, it is very important to understand the timing diagram, and we will discuss it there also. For a glance, just have a look. Propagation delay is important. You can see here. So just a glance in the sequential circuit, these all things will be used, and also for designing ROM and all these things, all these elements. Okay, and in this way our basic circuit will be done. Okay, thank you so much.